Welcome to a lesson on solving systems of linear equations using the addition method, also referred to as the elimination method. This method gets its name because the idea is we want to add the two equations together, and when we do this, either the x terms or y terms will be eliminated, which will allow us to solve for one of the variables, and then we can perform back substitution to determine the value of the other variable. Before we formalize the steps, let's consider this system here, and let's add the two equations together. So if we add the two equations together, we would have 1x plus 5x, that's 6x. But notice for the y terms, we'd have negative 2y plus 2y, which is 0. So when we add the equations together, notice how here the y terms are eliminated. And now you can see where this method gets its name. And on the right side, we have negative 11 plus 5, that's negative 6. Here we can solve for x by dividing both sides by 6. So we get x equals negative 1. So for our solution, which we know is an ordered pair, the first value of the ordered pair would be negative 1. And now to find y, because we know x equals negative 1, we can substitute negative 1 for x into either of the original equations. If we use the second equation, we'd have 5 times negative 1 plus 2y equals 5. Negative 5 plus 2y equals 5. So adding 5 to both sides, we have 2y equals 10. Dividing both sides by 2, we have y equals 5. So the ordered pair solution is negative 1 comma 5. But to verify our solution, we'd have to verify this ordered pair satisfies both of the original equations. And let's go ahead and do that. So we'll substitute negative 1 for x and 5 for y. So for the first equation, we'd have negative 1 minus 2 times 5 equals negative 11. Negative 1 minus 10 equals negative 11, which notice is true. So it satisfies the first equation. For the second equation, we'd have 5 times negative 1 plus 2 times 5 equals 5. Negative 5 plus 10 equals 5, which again is true. So our solution is correct. But notice how this whole process worked because when we added the equations together, the y terms were opposites. And most of the time, neither the x terms or y terms will be opposites, so we'll have to manipulate the equations in order for this to work. So let's solve this system here using the addition method, and we'll follow the steps outlined above. Step 1 says to line up the variables, meaning we want the x terms, y terms, and constants to be lined up vertically, which we have. Again, x terms, y terms, constants. Step 2 is the most important step. Determine which variable to eliminate and make the coefficients opposites. So looking at our system, notice how here we have a 4x. So if this was negative 4x, the x terms would be opposites. So if we want this x term to have a coefficient of negative 4, we can do that by multiplying both sides of the second equation by negative 4. So we're going to take this second equation and multiply both sides by negative 4. Notice how if we wanted to eliminate the y terms, they do have the opposite sign, but since the least common multiple of 3 and 5 is 15, we'd have to multiply the first equation by 5 and the second equation by 3. So by eliminating the x terms, we only have to multiply one of the equations by a constant, not both. But either method would work. So we'll keep the first equation the same because we're going to eliminate x. So we have 4x minus 3y equals negative 15. For the second equation, if we multiply by negative 4, we're going to have negative 4x and then minus 20y equals negative 8. Don't forget we're multiplying both sides of the equation by negative 4. Step 3, we add straight down. One variable should be eliminated. So we'll add the equations together. Because the x terms are opposites, this sum is 0. Here we have negative 3y plus negative 20y, that's negative 23y, equals negative 15 plus negative 8 or minus 8 equals negative 23. So step 4, we want to solve the resulting equation. So we'll divide both sides by negative 23. Simplifying, we have y equals 1. So for our ordered pair solution, which should be in the form x comma y, we know the second value is positive 1. So now we substitute this result into either original. Step 5 says substitute this result into either of the original equations, and then step 6, solve for the variable to find the ordered pair solution. Now that we know y equals 1, let's substitute y equals 1 into our second equation here. So using our equation x plus 5y equals 2, we substitute 1 for y, so we have x plus 5 times 1 equals 2, x plus 5 equals 2. Subtracting 5 on both sides, x equals negative 3. So our ordered pair solution is negative 3, comma 1. To verify our solution, we'll substitute x equals negative 3 and y equals 1 into both of the original equations. So for the first equation, we'd have 4 times negative 3 minus 3 times 1 equals negative 15. Negative 12 minus 3 equals negative 15. So this checks. And now for the second equation, we would have negative 3 plus 5 times 1 equals 2. Negative 3 plus 5 equals 2, which again is also true. So our solution is correct. It does satisfy both linear equations. Example 2, step 1, line up the variables, which is already done. We have the x terms, the y terms, and the constants. Step 2, determine which variable to eliminate. Make the coefficients opposites. Well, notice here, if we multiply the first equation by 4, we'd have a negative 8y here, and we have a negative 8y here. So because we want the terms to be opposites, we want this to be positive 8y, which means if we multiply the first equation by negative 4, the y terms would be opposites. If we wanted to eliminate the x terms here, the least common multiple of 3 and 5 would be 15. So we'd have to multiply both equations by a constant. For example, we could multiply the first equation by negative 5 to get negative 15x here, and multiply the second equation by positive 3 to get positive 15 here. But by multiplying the first equation by negative 4, the y terms would be opposites. So we can make the y terms opposites by multiplying just one of the equations by a constant. So let's eliminate the y's. So multiplying both sides of this first equation by negative 4, we'd have negative 12x plus 8y equals negative 12 times negative 4 is positive 48. Second equation stays the same. Step 3, add the equations. Negative 12x plus 5x is negative 7x. 8y plus negative 8y is 0. So we have negative 7x equals, this would be 56. Dividing both sides by negative 7, we get x equals negative 8. So for our ordered pair solution, which should be in the form x comma y, we know the first value is negative 8. Step 4 we already did, we just solved the resulting equation. So now for step 5, we substitute this result into either original equation, and then step 6, solve to determine our ordered pair solution. So let's go ahead and substitute negative 8 for x in, let's say, the first equation. So we'd have 3 times negative 8 minus 2y equals negative 12. So negative 24 minus 2y equals negative 12. Adding 24 to both sides, we'd have negative 2y equals positive 12. Dividing both sides by negative 2, we get y equals negative 6. So the ordered pair solution is negative 8 comma negative 6. Let's verify our solution. So we'll substitute negative 8 for x and negative 6 for y. So in the first equation, we have 3 times negative 8 minus 2 times negative 6 equals negative 12. So we have negative 24 plus 12 equals negative 12, which checks. Negative 12 equals negative 12. The second equation, we have 5 times negative 8 minus 8 times negative 6 equals 8. So we have negative 40 plus 48 equals 8, and 8 equals 8, so this also checks. Let's look at one more example. Step 1, line up the variables. We have the x terms, the y terms, the constants, so that's done. Step 2, determine which variable to eliminate, and make the coefficients opposites. Looking at the x terms, because the least common multiple of 3 and 7 is 21, to eliminate x, we'd have to make one of the coefficients positive 21 and the other negative 21. Looking at the y terms, because the least common multiple of 2 and 5 is 10, to eliminate the y terms, we have to have a coefficient of positive 10 for one term and negative 10 for the other. Let's eliminate the y terms. So let's multiply the first equation by positive 5. That would make this term negative 10y. So to make the y term here positive 10y, we have to multiply by negative 2. So here we have to multiply both equations by a constant to make the y terms opposites. So for the first equation, we'd have 35x minus 10y equals 41 times 5 is equal to 205. The second equation, multiplying by negative 2, we'd have negative 6x plus 10y equals negative 2. And now for step 3, we add the equations. So here we have 35x minus 6x, 29x. The y terms are opposites, so this sum is 0. Equals 205 minus 2 is 203. Dividing both sides by 29. 203 divided by 29 is equal to 7. So for our ordered pair solution, x comma y, we know the first value is 7. So we just completed step 4. Step 5, we substitute the result into either of the original equations. So let's substitute 7 for x in our first equation. So using 7x minus 2y equals 41, we'd have 7 times 7 minus 2y equals 41. Simplifying, 49 minus 2y equals 41. Subtracting 49 on both sides, we'd have negative 2y equals negative 8. Dividing both sides by negative 2, we have y equals positive 4. So for step 6, the ordered pair solution is 7 comma 4. Let's go ahead and verify our solution by substituting x equals 7 and y equals 4 into our equations. So the first equation, we'd have 7 times x, which is 7, minus 2 times y, which is 4, equals 41. 49 minus 8 equals 41, which is correct. This checks. And for the second equation, we'd have 3 times 7 minus 5 times 4 equals 1. We have 21 minus 20, and we have 1 equals 1. So once again, our solution is correct. Okay, I hope you found this helpful. We want to solve the system of equations using the elimination method, sometimes called the addition method. To solve a system of equations, we're looking for an ordered pair or an x and y value that would satisfy both of the equations. But we should also keep in mind that when solving a system of linear equations, it is possible to have no solution as well as an infinite number of solutions. Now the idea of the elimination method is we want to add these two equations together and eliminate either the x terms or the y terms. So if we want to sum the two equations and eliminate one of the variables, either the x terms or the y terms must be opposites. So looking at our two equations, notice how both the x terms and the y terms are the same. So if we want them to be opposites, we'd have to have either the x terms or y terms to be negative. So let's go ahead and multiply the first equation by negative 1. That's just going to change the sign of every term. So we'd have negative 5x minus 2y equals negative 4. In the second equation, we leave the same because notice how now, in this case, both the x terms and y terms are opposites. So this is one of those unusual cases because now when we add these two equations together, notice how the sum of the x terms is 0, but so is the sum of the y terms. So both the x terms and the y terms have a sum of 0, so we're left with 0 equals negative 6. So when we solve a system algebraically, meaning by the elimination method or the substitution method, and the variables are eliminated, this means the system will have either no solution or an infinite number of solutions. And it's based upon whether this given equation is true or not. Here we have 0 equals negative 6. Well, that's obviously false. 0 does not equal negative 6. And since this result is false, that means the system has no solution. And a way to verify this would be to graph these two linear equations, and when solving a system by graphing, the point of intersection would represent the solution. If we graph these two lines, notice how they're parallel, which means they don't intersect, verifying the system of equations has no solution. We want to solve the system of linear equations using the elimination method, sometimes called the addition method. To solve a system of equations, we want to find the ordered pair, or the x and y value that satisfy both equations. But we should keep in mind it's possible to have no solution, or even an infinite number of solutions, to a system of linear equations. Now, to use the elimination method, the idea is to add the two equations together, and in doing so, eliminate either the x terms or the y terms. Well, if we want the sum of the x terms or y terms to be 0, either the x terms or y terms must be opposites. So the first step in using the elimination method is to put the two equations in standard form, meaning we want the x terms and y terms on the left and the constant on the right. So notice the first equation is already in standard form, so we'll go and just leave this one as is. We have 2x minus 5y equals 4, but for the second equation we'll have to subtract 5y on both sides, so we would have 2x minus 5y equals 4. Now this is kind of an unusual case because if we take a look at these two equations, they're exactly the same. So this should already tell us about the solution to the system of equations. But let's just say we didn't recognize this. We know we want either the x terms or y terms to be opposites. Notice right now they're exactly the same. So if we want them to be opposites, we'd have to multiply one of the equations by -1. Let's just go ahead and multiply the first equation by -1 and then see what happens. We'll leave the second equation the same. So multiplying by -1 is just going to change the sign of everything. So we'll have -2x plus 5y equals -4. Second equation is going to stay the same. And now watch what happens when we add these two equations together. Well, the x terms and y terms are both opposites, so both sums would be 0. And on the right side we have -4 plus 4, that would also be 0. So when solving a system of equations algebraically, meaning by the elimination method or substitution method, if the variables simplify out, if the remaining equation is true, we have an infinite number of solutions, and if it's false, we have no solution. Well, 0 equals 0 is always true, which indicates that the system of equations has an infinite number of solutions. And that should make sense because, remember, to solve a system of linear equations, graphically, we're actually looking for a point of intersection where the coordinates of that point would be our solution. But if these two linear equations are the same, and then we graph both, it's going to be the same line twice, and therefore the lines would have an infinite number of points in common. So it is important to be aware of what happens algebraically when there's an infinite number of solutions, as well as if there is no solution. Again, if there was no solution, this equation here would be false. But in this case it's true, so we know we have an infinite number of solutions.